A ghostly whisper of heat fills the entire sky, the cooled remnant of the universe's explosive birth. This is the cosmic microwave background, the oldest light we can see, and it holds the secrets to our cosmic origins. By the end of this journey, you will understand how scientists learned to read this ancient map, tracing faint clues back to the first moments of everything. We will uncover how a uniform glow of light reveals the seeds of galaxies and the existence of mysterious dark matter and dark energy. What do you think it means to see the face of the infant universe? To detect a whisper, you need an instrument of profound silence. This is the first paradox of cosmic archaeology. The story begins not in space, but in a small town on Earth, with a device that was never meant to look at the sky. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent and baffling noise in a giant horn-shaped antenna built for satellite communication. It was a constant, low hiss that came from every direction, day and night, and no amount of cleaning, not even the removal of a family of pigeons nesting inside, could eliminate it. They had stumbled upon the afterglow of creation itself, a relic from a time when the universe was a glowing plasma of intense light. This uniform sea of radiation, now cooled to just a few degrees above absolute zero, is the cosmic microwave background. It is the oldest photograph ever taken, a baby picture of the cosmos when it was a mere 380,000 years old. But a perfectly uniform glow tells only half the story. The true magic, the evidence for the seeds of galaxies, lies in the tiny variations within that light, variations almost too small to measure. Yet that very perfection posed a new and profound puzzle. A perfectly smooth universe is a universe without a future, without us. If the cosmic microwave background were truly uniform, then the matter in that infant cosmos would have been spread with impossible evenness. There would have been no clumps of slightly denser material, no gravitational seeds from which galaxies, stars, and planets could ever grow. The cosmos would have remained a vast, dark, and empty sea of atoms. So where did the structure we see all around us come from? The answer was hidden in the details, in deviations so tiny they seemed almost impossible to detect. Finding them would require a new kind of mission, one that had to rise above the blurring effects of our own atmosphere to see the ancient light with absolute clarity. This led to one of the most ambitious experiments ever conceived, a satellite designed to listen to the echo of the Big Bang with a sensitivity beyond anything previously possible. Its goal was to map the entire sky and measure the temperature of the cosmic background down to a few millionths of a degree. What it found would change everything. The quest to find these cosmic seeds became a race against technological limits. That uniform glow Penzias and Wilson discovered was, in fact, not perfectly smooth at all. It is imprinted with incredibly faint patterns, variations in temperature so small they are almost beyond belief. These anisotropies, as they are called, are deviations of just 1 part in 100,000. To put that into perspective, if the cosmic microwave background were an ocean, these anisotropies would be ripples no taller than a single sheet of paper compared to the depth of the sea. Yet, within these minuscule hot and cold spots lies the entire blueprint for our cosmic home. They are the fossilized imprints of the universe's earliest moments, the gravitational seeds that would one day blossom into everything we see. Think of a slightly denser patch of that primordial plasma. It held just a little more gravitational pull, acting like a well that other matter would slowly fall into over billions of years. In the cosmic microwave background, we see these denser regions as slightly cooler spots. This is because photons of light, fighting their way out of a stronger gravitational field, lost a tiny bit of energy, shifting their color ever so slightly toward the cooler end of the spectrum. The precise pattern of these spots across the sky is like a unique cosmic fingerprint. It does not just tell us where galaxies would form, it encodes the fundamental recipe of the universe itself. The size and distribution of these anisotropies reveal the total amount of matter, the nature of dark energy, and even the geometry of spacetime. But capturing this fingerprint required a view far clearer than any telescope on Earth could provide. Our atmosphere, a protective blanket of air, acts like a shimmering curtain, blurring the subtle details of this ancient light. To see the infant universe in sharp focus, we had to go above it all. The next great leap would not come from a mountaintop, but from a satellite launched into the cold, silent vacuum of space, tasked with mapping the oldest light with unparalleled precision. The answer arrived in the cold, silent expanse of space. In 1989, a Delta rocket carried NAS, a Cosmic Background Explorer, or COBE, into orbit. Its singular purpose was to listen to the universe's oldest whisper with a clarity never before achieved. Shielded from the warm hum of our planet and the distortions of its atmosphere, COBE instruments were cooled to within a few degrees of absolute zero. This was not just a satellite, it was the most sensitive thermometer ever built, designed to measure the heat of the cosmic dawn across the entire sky. The data it sent back was nothing short of revolutionary. First, it confirmed with stunning precision that the cosmic microwave background has the perfect spectrum of a blackbody, a hallmark of radiation born in the thermal equilibrium of a hot, dense beginning. This confirmation alone was a monumental triumph, solidificating our understanding of the Big Bang and earning the mission's lead scientists the Nobel Prize. But COBE's true gift to humanity was a map. After meticulously scanning the heavens, it produced the first full sky image of the cosmic microwave background's tiny temperature variations. For the first time, we could see the cosmic blueprint with our own eyes. The map revealed a universe that was overwhelmingly smooth, just as Penzias and Wilson had found, but etched across that smoothness were the faintest of ripples. These were the anisotropies, the seeds of all future structure. The lead project scientist, John Mather, described the moment of discovery with awe, saying it was like seeing the face of God. And in a scientific sense, it was. We were looking at the gravitational fingerprints that would one day sculpt the great cosmic web of galaxies. Yet, for all its glory, the COBE map was like viewing a masterpiece painting through a thick pane of frosted glass. You could see the grand composition, the broad strokes of hot and cold, but the fine details, the sharp edges that held the universe's deepest secrets, remained blurred. The hunt was on for a successor, a mission with vision sharp enough to read the fine print on the birth certificate of the cosmos. The frosty glass of the COBE map needed to be replaced by a perfect lens. That lens arrived in the form of the Wilkinson Microwave Anisotropy Probe, known as WMAP, a spacecraft launched in 2001 with a singular, profound mission. It was designed not just to see the ripples in the cosmic background, but to measure their exact size, shape, and distribution with a precision that was almost unimaginable a decade before. Where COBE saw a blurry impression of the cosmic fingerprint, WMAP was tasked with reading every single ridge and whorl. For 9 years, WMAP observed the sky from a special gravitational balancing point 1 million miles from Earth, a location of profound quiet and stability. Its instruments, far more sensitive than COBE, scanned the cosmic microwave background with a resolution so sharp, it was like comparing a child's sketch to a high-definition photograph. The map it sent back was breathtaking. It showed the entire sky painted with a cosmic leopard spot pattern of hot and cold regions, a detailed chart of the universe's original density variations. But the true revolution was not just in the picture's beauty. It was in the numbers. By analyzing the precise statistical properties of these spots, cosmologists could perform what amounted to a cosmic blood test, determining the fundamental ingredients of the universe with astonishing accuracy. The data revealed a universe that is 13.77 billion years old, a number pinned down with a certainty of just a few tens of millions of years. It precisely measured the cosmic recipe. We learned that everything we can see and touch, all the stars, planets, and galaxies, constitute a mere 5% of the universe. 27% is the invisible gravitational glue of dark matter, and a staggering 68% is the mysterious repulsive force of dark energy. WMAP also made a critical measurement about the shape of the cosmos. The geometry of the universe on the largest scales was found to be flat to within a razor-thin margin of error of just 0.4%. This flatness is a direct prediction of the theory of cosmic inflation, the idea that the universe underwent a period of hyper-expansion in its first fraction of a second. WMAP findings cemented the lambda cold dark matter model as the standard, accepted picture of our universe. It was a monumental achievement, a culmination of decades of work. Yet, in answering so many questions, WMAP exquisite map revealed new levels of subtlety in the ancient light. It proved that if we listened even more closely, the universe still had more to say. But the universe's whisper holds more information than just its temperature. Planck's mission was to listen for the subtle polarization of this ancient light, a faint directional imprint left on the photons as they scattered in the primordial plasma. This polarization is a ghostly signature of the universe's very first tremors, gravitational waves that rippled through the fabric of spacetime during the initial violent burst of inflation. While the main evidence for these waves remains an active and challenging frontier of research, Planck's data placed crucial limits on their expected strength, further refining our picture of the universe's explosive birth. The satellite's legacy is a paradox of profound knowledge and deepening mystery. It gave us our most precise cosmic recipe, confirming that ordinary matter makes up just under 5% of the universe, dark matter about 27%, and dark energy about 68%. Yet, within this exquisitely detailed map, Planck found strange, large-scale anomalies. One is a mysterious cold spot, a region of the sky significantly cooler than the standard model can easily explain. Another is an unexpected lopsidedness in the temperature fluctuations, a cosmic asymmetry that hints at a preferred direction in the universe, a concept that challenges our fundamental assumption of isotropy. These are not errors, they are real features in the data, and they stand as quiet but persistent clues that our understanding of the cosmos, for all its sophistication, is not yet complete. They are the faint echoes of processes we have not yet begun to imagine, pointing toward the next great mystery, the very mechanism that set this entire cosmic story in motion. The Planck satellite's anomalies whisper of a deeper mystery, the very trigger for the cosmic story we have been tracing. To understand how those faint ripples in the cosmic microwave background came to be, we must journey back to a time even more remote than the release of the first light. We must venture into the universe's first fleeting moments, to a theory that addresses the most profound questions head-on. Why is the cosmos so large and so uniform? And where did the seeds for galaxies even come from? The answer lies in a concept of almost unimaginable power called cosmic inflation. This theory proposes that in the first sliver of a second after the Big Bang, far less than a trillionth of a trillionth of a trillionth of a second, the universe underwent a violent, exponential growth spurt. It did not just expand, it inflated, doubling in size repeatedly at a rate faster than the speed of light. In this incredibly brief period, a subatomic speck of space-time was stretched to a size larger than our entire observable universe today. This explosive stretching acted like a cosmic iron, smoothing out any primordial wrinkles and knots to an incredible degree. This is why the cosmic background radiation appears so remarkably uniform from one end of the sky to the other. But inflation did more than just create smoothness, it also created the seeds of structure. Even in that primordial speck, empty space was not truly empty. It was a seething quantum foam, bubbling with tiny, unpredictable fluctuations in energy. These quantum jitters were microscopic, normally fading in and out of existence far too quickly to matter. But inflation grabbed these fleeting fluctuations and stretched them across the cosmos, freezing them into permanent, macroscopic imprints on the fabric of space. A tiny region of slightly higher density, inflated to a colossal scale, became one of those slightly denser patches we see as a cold spot in the cosmic microwave background. The gravitational well was born. The theory of inflation is not just a wild idea. It makes very specific, testable predictions about the kind of pattern these stretched quantum seeds should create. It predicts a particular statistical distribution of hot and cold spots, a specific fingerprint of their sizes and correlations across the sky. And when scientists like those on the Planck mission compared their exquisitely detailed map to these predictions, the match was nothing short of spectacular. The observed pattern of anisotropies aligns with the predictions of inflation with stunning precision. This is how we move from theoretical mathematics to tangible evidence, by finding the unique signature that a theory leaves on the oldest light in the universe. Yet, for all its success, inflation is not a single, simple story. It is a framework, a class of models that all point to an initial inflationary burst. The precise details of what drove this expansion, the nature of the inflatoned field that powered it, remain one of the greatest puzzles in physics. The confirmation of the basic inflationary picture brings us face to face with the next frontier, a realm where the universe's largest structures are connected to its smallest possible scales. Yet the temperature map, for all its detail, is only one layer of the story. The ancient light of the cosmic microwave background carries a second, more subtle message encoded in its very orientation, a property known as polarization. Think of the light from the young universe not just as a wave of energy, but as a wave with a specific direction, like a rope you can shake up and down or side to side. This polarization is a fossilized record of the very last moments before the light was set free. In the searing plasma of the early cosmos, photons of light were constantly bouncing off free electrons, a process called Thomson scattering. This final scattering event, as the universe cooled enough for atoms to form and the electrons to be captured, imprinted a specific directional signature on the escaping light. It is a whisper within the whisper, a faint pattern that tells us about the motion and distribution of matter in those final instants of the cosmic fireball. Scientists have learned to read this polarized light, and they have identified two distinct patterns, like different handwriting styles in the cosmic record. The first are called E-modes. These are curling patterns like the field lines around a magnet that are generated by the same density fluctuations that created the hot and cold spots in the temperature map. The successful mapping of E-mode polarization provided a powerful and independent check on the findings from the temperature data, confirming the entire story of gravitational seeds and cosmic structure. But the second type of pattern, known as B-modes, is the true holy grail of modern cosmology. These are a swirling, curl-like pattern, much harder to produce. One source of B-modes comes from a cosmic illusion. As the ancient light travels for billions of years to reach us, its path is gently bent by the gravitational pull of all the matter, both dark and visible. It passes along the way. This effect, called gravitational lensing, can twist the simpler E-mode patterns into the more complex B-mode signature. Detecting these lensing-induced B-modes is a remarkable achievement in itself, as it allows us to create a map of the distribution of all the matter in the universe, tracing the invisible cosmic web of dark matter. But there is another, far more profound potential source for B-modes, one that takes us back to the very first instant of inflation. The theory predicts that the violent, exponential stretching of space-time itself would have generated ripples in the fabric of the cosmos, primordial gravitational waves. Just as a shaking motion can polarize light, these colossal space-time tremors would have imprinted a unique, swirling B-mode pattern directly onto the cosmic microwave background. Finding this primordial B-mode signal would be the ultimate smoking gun for inflation. It would be a direct observation of the universe's birth pangs, a measurement of the incredible energy scale at which our entire reality began. The hunt for this faint, swirling signature is now one of the most intense and challenging endeavors in all of science, pushing our instruments to the very edge of what is possible. The hunt for this primordial swirl is a battle against an almost impossibly faint signal. The B-mode polarization created by inflation's gravitational waves is predicted to be extraordinarily weak, a temperature variation on the order of just 1/10,000,000th of a degree. Finding it is like trying to hear a single feather drop in a hurricane. To even attempt this, scientists have built some of the most sensitive detectors on the planet, and they have placed them in the most extreme environments on Earth. High on the Antarctic plateau at the South Pole, the air is so cold and dry that it is almost as transparent as space itself. Here, experiments with names like BICEP and the Keck array, and the next generation Simon's Observatory, point their arrays of cryogenically cooled detectors toward a single, pristine patch of sky, observing it year after year. They are listening for the faintest whisper of a pattern, a cosmic signature that has traveled for over 13 billion years to reach us. But there is a formidable obstacle in their way, a contaminant that mimics the very signal they are seeking. Our own galaxy is filled with cosmic dust, microscopic grains of silicon and carbon that are also polarized. As these dust particles align with the Milky Way's magnetic field, they emit their own polarized light, which can create a B-mode pattern that is virtually indistinguishable from the primordial one. This galactic dust is the ultimate cosmic spoiler, a foreground fog that must be seen through with absolute precision. The story of this search took a dramatic turn in 2014, when the BICEP-2 team announced a potential discovery. They believed they had found the telltale swirl of primordial gravitational waves. The excitement was palpable, a potential Nobel Prize-level breakthrough. But further analysis, in collaboration with data from the Planck satellite, revealed a sobering truth. The signal they detected was overwhelmingly dominated by this polarized dust from our galaxy. It was a lesson in humility and the relentless rigor of science. The quest did not end there, it evolved. The challenge now is to separate the cosmic signal from the galactic noise with ever greater accuracy. This requires building even more sensitive instruments and creating exquisitely detailed maps of the galactic dust itself, so it can be subtracted from the data. The search continues, a meticulous process of elimination in the hope of isolating the universe's very first tremor, a ripple from the dawn of time. This galactic dust is the ultimate cosmic spoiler, a foreground fog that must be seen through with absolute precision. The challenge is not merely one of sensitivity, but of identity. The polarized light from these microscopic dust grains, shaped by the Milky Way's magnetic fields, creates a swirling B-mode pattern that is virtually a perfect doppelganger for the signal we are trying to find. They are cosmic twins separated at birth, one born in the violent first instant of creation, the other a local product of our own galaxy's slow evolution. Telling them apart requires a subtle but crucial difference: their color. Just as a red object and a blue object might look the same in a black and white photograph, the cosmic microwave background and the galactic dust glow most brightly at different wavelengths of light. The ancient light from the Big Bang has a very specific spectrum, while the dust shines with a different signature. To separate them, you must take a color picture of the sky across many different frequencies. This is where the Planck satellite became an unexpected hero in the hunt. While it was mapping the cosmic microwave background, it was also creating the most detailed all-sky atlas of this galactic dust ever produced. Planck's multi-frequency view revealed that the dust is not a uniform haze, but a complex, dynamic tapestry. It is more pervasive, more variable, and more polarized than anyone had fully appreciated. This was a sobering but essential revelation. It meant that any claim of discovering primordial B modes would have to be backed by an ironclad case, with the dust's contribution measured and subtracted with surgical accuracy. The quest now demands a new generation of observatories, like the Simons Observatory and the proposed LiteBIRD satellite, designed from the ground up to observe at many frequencies simultaneously. They will act as cosmic spectrometers, analyzing the light's color with such precision that the dust's faint glow can be digitally peeled away, layer by layer, hoping to reveal the pristine signal of inflation hidden beneath. This painstaking process is a testament to the fact that to hear the universe's first whisper, we must first learn to silence the hum of our own galactic home. The ancient light of the cosmic microwave background is our starting point, but the story does not end there. To truly understand the universe's growth, we must look at the colossal architecture it has built over billions of years. This is the large-scale structure of the cosmos, a vast cosmic web of galaxies, clusters, and immense empty voids. It is the adult phase of the universe, the direct result of those tiny seeds seen in the infant's photograph. Mapping this web is an undertaking of almost unimaginable scale. Projects like the Sloan Digital Sky Survey have spent decades systematically scanning the sky, not to look at individual galaxies, but to plot their positions with meticulous care. The result is a three-dimensional map of the nearby universe, a chart that reveals a delicate, filamentary structure, like a sponge or a network of neurons on a cosmic scale. Galaxies are not scattered randomly. They are strung along these invisible threads of dark matter, gathered at dense intersections and separated by vast, dark deserts of empty space. How do we connect this mature cosmic city to its humble beginnings? The key lies in frozen sound waves from the dawn of time, known as Baryon acoustic oscillations. In the first 400,000 years, the universe was a hot, dense plasma, a fluid where light and matter were locked together. In this primordial soup, gravity tried to pull matter into the denser seeds, but the intense pressure of the trapped radiation created powerful counteracting waves, like sound waves ringing through the cosmic fluid. Then, at the moment of recombination when atoms formed and the universe became transparent, these sound waves were instantly frozen in place, imprinting a specific scale on the distribution of matter. Think of it as a cosmic ruler, a standard length stamped onto the universe when it was just a baby. This ruler is about 500 million light-years long. As the universe expanded, this preferred scale stretched along with it. Today, when we look at our galaxy maps, we can detect this same ruler. We see a subtle but statistically significant preference for galaxies to be separated by this specific distance, a faint echo of that primordial sound. It is a direct link, a fossilized ripple that connects the map of the infant universe from the cosmic microwave background directly to the map of the adult universe from galaxy surveys. This provides a powerful cross-check of our entire cosmic model. The growth of this structure from quantum jitters to a vast web, however, is not driven by what we see, but by what we cannot. The rate at which galaxies clump together, and the way the cosmic web forms is governed by the relentless pull of dark matter and the countervailing push of dark energy. By measuring the precise details of the large-scale structure, we are essentially taking the universe's temperature, testing the very laws that have shaped everything from the first instant to the present day. This invisible majority, dark matter, acts as the universe's fundamental skeleton, while the cosmic microwave background reveals the blueprint, Dark matter provided the gravitational framework necessary to build upon it. Think of the early universe after the release of the first light. Ordinary matter, the protons and electrons that make up everything we see, was now a hot, diffuse gas. It was simply too energetic, too spread out, and too susceptible to the pressure of radiation to collapse under its own gravity. It needed a guide, a pre-existing structure to show it the way. Dark matter was that guide. Because it does not interact with light or other matter in any way except through gravity, it was immune to these pressures. While normal matter was buffeted by the fading echoes of the Big Bang, dark matter could quietly begin to coalesce, pooling into vast, invisible clouds under the relentless pull of its own gravity. These clouds became the gravitational wells, the cosmic basins, into which the hot gas of ordinary matter could later settle and cool. The pattern of anisotropies in the cosmic microwave background is exquisitely sensitive to this dynamic. The size and distribution of the hot and cold spots we see are a direct reflection of how much dark matter was present to orchestrate the formation of structure. Without its dominant gravitational influence, the subtle ripples in the primordial plasma would not have grown into the grand cosmic web we observe today. The universe would have remained a formless, expanding haze of atoms. So when we measure the precise statistical properties of that ancient light, we are not just mapping the seeds of galaxies, we are taking an inventory of the invisible material that made their growth possible. The cosmic microwave background tells us that dark matter is cold, meaning it moved slowly in the early universe, allowing small structures to form first. It tells us there is about 5 times more dark matter than ordinary matter. This invisible scaffolding is not a minor component. It is the primary architect of the visible cosmos. But the cosmic web tells a story with 2 competing forces. While dark matter's relentless pull builds the grand structures, another, more mysterious component is working in opposition, shaping the universe on the largest scales of all. This is the enigma of dark energy. For most of the 20th century, scientists assumed the universe's expansion, set in motion by the Big Bang, was gradually slowing down. It seemed logical that the collective gravitational pull of all the matter in the cosmos would act as a brake, slowly reining in the outward rush. Then, in the late 1990s, 2 independent teams studying distant supernova made a shocking discovery. The universe's expansion is not slowing down at all. It is accelerating. Something is actively pushing galaxies apart, and that something has been named dark energy. It is a repulsive force that makes up a staggering 68% of the universe, and its fingerprint is etched into the ancient light of the cosmic microwave background. The connection is not direct, but incredibly powerful. Dark energy influences how we see the baby picture of the universe. Specifically, it changes the apparent size of the hot and cold spots on the map. Think of the cosmic microwave background as a distant screen, a surface of last scattering fixed at a certain distance in time, when the universe was only 380,000 years old. The actual physical size of the ripples on that screen is determined by physics we understand well, set by how far sound could travel in the primordial plasma. This gives us a known, standard ruler, but how big that ruler appears to us today, its angular size on our sky, depends on the geometry of the universe between then and now. If dark energy has been causing the expansion to accelerate, it means the universe has stretched more than we would have expected in a matter-dominated cosmos. This extra stretching affects the path that the ancient light takes to reach us, effectively placing the surface of last scattering farther away. When you look at an object that is farther away, it appears smaller. The accelerating expansion driven by dark energy makes the entire cosmic microwave background pattern appear slightly smaller on the sky than it would otherwise. The precise measurement of the angular size of the anisotropies, first by WMAP and then with exquisite accuracy by Planck, revealed this very effect. The spots were the exact right size to confirm that the universe is geometrically flat, but their scale also demanded the presence of dark energy to explain the observed acceleration. This is how the oldest photograph we possess also reveals the universe's ultimate fate. The same faint whispers that seeded the galaxies now tell us that those galaxies are flying apart from one another faster and faster, driven by a force whose nature remains one of the greatest mysteries in all of science. Yet to understand the universe just before that first light, we must peer into an even earlier, more violent chapter. The story of the cosmic microwave background truly begins in the first few minutes of everything, when the entire cosmos was a fleeting, primordial fusion reactor. In that initial blaze, the fundamental building blocks of matter were forged. Protons and neutrons, freshly formed from the quark-gluon plasma, buzzed through a universe so hot and dense that nuclear reactions occurred everywhere at once. For a brief window, from about 1 second to 3 minutes after the Big Bang, the conditions were perfect for these particles to collide and stick together, forming the first atomic nuclei. This epoch is known as Big Bang Nucleosynthesis, the origin of the simplest elements. The process was a frantic race against the clock, as the universe expanded and cooled with incredible speed. First, protons and neutrons combined to form deuterium, a heavy isotope of hydrogen. This deuterium then rapidly fused into helium-4, the most stable light nucleus. The frantic dance of fusion produced primarily hydrogen and helium, with only the tiniest trace of lithium. Then, as the universe cooled past 1 billion degrees, the nuclear fires died down. The density dropped too low for further fusion, freezing the elemental abundances in place. The entire recipe for the ordinary matter in the cosmos was set in those first 180 seconds. What makes this story so powerful is that it makes a very specific prediction. The theory of Big Bang nucleosynthesis calculates precise percentages for how much of the universe should be hydrogen, helium, and lithium, based on the density of matter and the rate of expansion at that time. For decades, these predictions were just numbers on a page. Then, astronomers began looking at the most ancient objects we can find, stars in the halos of galaxies that formed from nearly pristine gas. They also observed distant, primordial clouds of gas that have never been touched by the nuclear furnaces of stars. When they measured the chemical composition of these cosmic fossils, the agreement was breathtaking. The observed abundances of helium and deuterium match the predictions of Big Bang nucleosynthesis with stunning, almost uncanny precision. This is not a rough estimate, it is a precise confirmation. This agreement is a cornerstone of modern cosmology, a second, completely independent line of evidence that points back to a hot, dense beginning. It tells us that our physical understanding of the universe is robust enough to be trusted back to within a single second of its origin. The success of nucleosynthesis gives us the confidence to push our models even further back, to the very limits of time itself. While the cosmic microwave background gives us a baby picture from 380,000 years after the Big Bang, an even older relic was created in the universe's very first second. This is the cosmic neutrino background, a sea of the most elusive particles known to science. Neutrinos are ghostly travelers, passing through almost everything in existence without a trace. They are so weakly interacting that trillions of them are streaming through your body every second, completely unnoticed. Their story begins at the 1-second mark, when the universe was still a searingly hot soup of particles. At that unimaginable temperature, neutrinos were constantly colliding with electrons and other particles, trapped in the dense cosmic fluid. But as the universe expanded and cooled in that first second, something pivotal happened. The density dropped to a point where neutrinos could no longer find anything to collide with. They suddenly decoupled from matter and began streaming freely across the cosmos, never to be significantly disturbed again. This happened long before the photons of the cosmic microwave background were set free. So while the CMB is an ancient photograph, the cosmic neutrino background is a fossil from an even more remote era. Detecting this fossil directly is a monumental challenge, as these relic neutrinos now have incredibly low energy. But we do not necessarily need to catch one to know they are there. Their collective presence has left a subtle, indelible mark on the cosmic microwave background we can already see. Think of the early universe as a race between different forms of energy. Before the release of the first light, the cosmos contained not just photons, but also this vast sea of neutrinos. This neutrino background contributed to the overall energy density of the universe, which in turn governed how fast it was expanding. More energy density means a stronger gravitational pull, slowing the expansion slightly. This change in the expansion rate during those first few 100,000 years had a direct consequence. It altered the way sound waves propagated through the primordial plasma, ultimately affecting the precise sizes and spacings of the hot and cold spots, the acoustic peaks, in the CMB power spectrum. By analyzing the intricate details of the CMB map with extreme precision, cosmologists can see the faint gravitational shadow cast by these relic neutrinos. It is like deducing the presence of a silent orchestra member by the subtle way they influence the music's rhythm. The data from the Planck satellite has already provided strong evidence for this effect, confirming that this cosmic neutrino background is real and that its properties align with our theoretical predictions. The next frontier is to move from this indirect evidence to a more direct measurement. Future experiments are being designed to try and capture these primordial neutrinos, an endeavor that would give us a pristine snapshot of the cosmos at the tender age of just 1 second old. The hunt for the universe's first whisper demands a new generation of listeners, instruments so sensitive they border on the impossible. While current observatories push the limits of technology from the high deserts of Chile to the frozen plains of Antarctica, the ultimate clarity may only be achieved beyond the veil of our atmosphere. The next great leap is taking shape in mission control rooms and laboratories around the world, in the form of cosmic detectives designed with one singular, profound goal: to capture the primordial swirl of gravitational waves, or to prove it is fainter than our boldest theories predict. Leading this charge from space is the LiteBIRD satellite, a mission spearheaded by the Japan Aerospace Exploration Agency, or JAXA. LiteBIRD, which stands for Light Satellite for the study of B-mode polarization and inflation from dust, is not a general-purpose observatory. It is a specialist, a master key crafted to unlock one specific door. Its entire design is optimized to hunt for the B-mode polarization pattern across the entire sky, with a sensitivity that dwarfs even the most advanced ground-based efforts. Its secret weapon is an unparalleled ability to see in color. LiteBIRD will observe the sky in 15 different frequency bands, from the low-frequency radio waves where the cosmic signal is strongest, to the higher frequencies where galactic dust shines brightly. This multi-frequency vision is like having a hyper-sophisticated set of filters, allowing scientists to perform a perfect digital subtraction of the Milky Way's foreground pollution. By analyzing the subtle color differences between the cosmic signal and the galactic dust, LiteBIRD aims to peel away the local interference and reveal the pristine, ancient pattern beneath, if it exists. Its mission is to either find the smoking gun of inflation or to tell us, with absolute certainty, that the simplest models of that explosive beginning are wrong. On the ground, the ambition scales to an entirely new level with the CMB-S4 project. Imagine not one telescope, but a coordinated network of them, stationed at the best observing sites on Earth. CMB-S4 plans to deploy an army of detectors, not thousands, but hundreds of thousands, all cryogenically cooled to a fraction of a degree above absolute zero. This colossal effort will map the cosmic microwave background with a depth and resolution that is simply unimaginable today. Where current experiments study small, pristine patches of sky, CMB-S4 will conduct a comprehensive, all-sky survey at a level of detail that will make the Planck map look like a rough sketch. This incredible precision is not just about seeing the B modes more clearly. It is about measuring every aspect of the CMB's temperature and polarization with such exquisite accuracy that we can probe for cracks in our standard model of cosmology. The data could reveal subtle statistical anomalies, strange correlations, or unexpected patterns that point toward physics we have not yet discovered. Perhaps it will find evidence for new types of neutrinos, or shed light on the nature of dark matter, or even hint at a time before the Big Bang. Together, these observatories represent a fundamental shift. We are no longer just mapping the cosmos, we are interrogating it. The journey from the faint echoes discovered by Penzias and Wilson to the detailed evidence compiled by Planck has brought us to the brink of a new understanding. The next generation of instruments will ask the universe its most profound questions directly. Did inflation really happen? What is the true nature of the energy that drove it? The answers, whether a clear detection or a confounding absence, will rewrite our story of cosmic origins. The journey from echoes to evidence is far from over. It is accelerating into a future where the faintest clues will finally tell their full story. Yet the breathtaking precision of our cosmic map reveals subtle cracks in the foundation. The standard model of cosmology, built on the pillars of the cosmic microwave background, is a triumph of modern science, but it is not perfect. Like a masterfully crafted watch that keeps excellent time yet gains a few seconds each year, the universe presents us with persistent anomalies, quiet whispers that something in our story may be incomplete. The Planck satellite, for all its clarity, found strange features on the largest scales of the cosmos. One is a mysterious cold spot, a region of the sky significantly cooler than our models can easily explain. If this were just a single quirk, we might dismiss it as a statistical fluke, a cosmic coincidence, but it is not alone. The entire pattern of the cosmic microwave background exhibits a curious asymmetry. The average temperature of one hemisphere of the sky is subtly different from the opposite hemisphere, as if the universe has a preferred direction, a concept that directly challenges our fundamental assumption that the cosmos is uniform and isotropic on the grandest scales. These are not errors in the data. They are real features etched into the oldest light we can see. They are the universe quietly suggesting that the rules we have written might need a footnote, or perhaps an entirely new chapter. An even more pressing puzzle lies in the very expansion rate of the universe today. By measuring the distance to nearby galaxies and the bright flashes of supernova, astronomers have pinned down a value for the Hubble constant, the speed at which the cosmos is expanding. But when we use the detailed blueprint of the cosmic microwave background to work backwards, applying our well-tested laws of physics to predict what the expansion rate should be today, we get a different answer. This discrepancy, known as the Hubble Tension, is a serious problem. It is not a small margin of error. It is a stubborn gap that has only widened with more precise measurements. It is as if you carefully calculated how fast a car should be going based on its acceleration from a standing start, only to find it is now moving significantly faster than your math allows. This tension might be the most exciting clue we have. It could be pointing toward new physics, something missing from our standard recipe. Perhaps an early form of dark energy gave the young universe an extra push. Maybe neutrinos, those ghostly particles, have exotic properties we have not yet discovered. These anomalies are not failures of the scientific method, they are its engine. They are the unanswered questions that drive observers to build more sensitive telescopes and theorists to dream bolder ideas. They remind us that our cosmic story, for all its detail, is a living document, still being written with every new observation. Inflation provides a powerful narrative, but it is not the final word. The very idea of a singular beginning, a moment of infinite density, pushes our laws of physics to a breaking point. This has led physicists to explore radical alternatives that rewrite the opening chapter entirely. Imagine a universe that did not begin with a bang, but with a bounce. In bouncing cosmologies, our expanding universe could be just one phase in an endless cycle of contraction and rebirth. A previous cosmos might have collapsed in a big crunch, only to rebound into the expansion we see today, carrying forward a faint memory of its past life. Another idea, string gas cosmology, proposes that the fundamental ingredients of reality are not points but tiny, vibrating strings. In this view, the early universe was a hot, dense gas of these strings, and its properties emerged from their complex statistical behavior, potentially avoiding a singularity altogether. These theories push our inquiry to the ultimate frontier, a time so early it is almost a metaphysical concept. This is the Planck epoch, the first 10 to the negative 43 seconds. To grasp this scale, consider that a single second contains more Planck times than there have been seconds since the Big Bang. In this realm, the energy was so immense that the fabric of space-time itself would have been a seething, foaming quantum mess. General relativity, which describes gravity and the smooth curvature of space, completely breaks down. To understand this epoch, we need a theory of quantum gravity, a framework that unifies the cosmic and the quantum. Two leading candidates offer profoundly different visions. String theory suggests that the fundamental particles are minuscule, vibrating loops, and that the universe may have many more hidden dimensions curled up into shapes too small to see. Loop quantum gravity, in contrast, proposes that space itself is not continuous, but is woven from a fabric of discrete, finite loops, like a pixelated screen on the smallest possible scale. These are not just mathematical curiosities. They make specific predictions about the nature of the primordial universe. For instance, some models of loop quantum gravity naturally lead to a bouncing scenario, replacing the Big Bang singularity with a big bounce. This is where the faint whispers of the cosmic microwave background become our only guide into this terra incognita. The pattern of hot and cold spots, the statistics of the anisotropies, and the elusive signature of primordial gravitational waves are all sensitive to the physics of the universe's first moments. If a theory of quantum gravity predicts that the initial quantum fluctuations had a certain character, that character would be imprinted onto the cosmic microwave background. A detection of primordial B-mode polarization, for example, would not only confirm inflation, but could also reveal the energy scale at which it occurred, offering a crucial clue about the underlying quantum gravity theory. The echoes of the Big Bang thus act as a cosmic archaeological dig, sifting through the possibilities. They constrain which grand, unifying theories could possibly be viable, connecting the largest structures we observe to the very smallest scales that can exist. Our journey from a faint hiss in a radio antenna is slowly building a bridge to the most fundamental laws of physics. This cosmic fine-tuning presents a profound and unsettling question. The fundamental numbers that govern our universe, the so-called constants of nature, appear to be set with an almost impossible precision. Consider the density of dark energy, the very force driving the cosmic acceleration. If this value were just slightly larger, the repulsive force would have been so powerful in the early universe that it would have torn apart the fragile gravitational seeds before galaxies could ever form. Matter would have been flung apart into a cold, dark, and eternal emptiness. Conversely, if dark energy were significantly weaker, the gravitational pull of matter would have quickly reversed the expansion, causing the entire cosmos to collapse back in on itself in a catastrophic big crunch, long before stars could ignite and planets could coalesce. The window for a universe that is both long-lived and structured is incredibly narrow. The same is true for the initial strength of those quantum fluctuations, the amplitude imprinted by inflation. If those primordial ripples had been much fainter, the gravitational wells would have been too shallow, and matter would never have clumped together into galaxies. The cosmos would have remained a featureless haze. If the fluctuations had been too strong, however, matter would have collapsed into a nightmare landscape of overwhelming black holes, with no stable solar systems possible. The universe seems balanced on a razor's edge, and this observation leads us directly to a deeply philosophical idea known as the anthropic principle. In its simplest form, it states that the universe we observe must be compatible with the existence of observers. We should not be surprised to find ourselves in a universe capable of producing life, because in a universe that was not, we would not be here to ponder the question. It is a statement that seems almost tautological, yet it carries significant weight when faced with the evidence for fine-tuning. But if our universe is just one possible outcome, why does it have these specific, life-permitting properties? One potential answer, emerging from the theory of inflation itself, is that our cosmos is not alone. The same mechanism of exponential expansion that smoothed our universe may be an eternal process, happening in different patches of a greater meta-universe. In this inflationary multiverse scenario, new bubble universes are constantly budding off, each with its own random set of physical constants and laws. Most of these bubbles would be stillborn or sterile, collapsing instantly or expanding into emptiness. But in a vast enough multiverse, every possible combination of constants will be realized somewhere. We do not live in a specially designed universe, but rather, we find ourselves in one of the rare bubbles where the numbers happen to line up correctly for galaxies, stars, planets, and ultimately for us. This idea is controversial, as it can feel like an untestable retreat from a deeper explanation. Yet, it represents a bold attempt to connect the immense scales of cosmic structure, governed by dark matter and dark energy, to the most intimate question of all, our own existence. It suggests that the faint whispers from the first moments may be telling a story far grander than we ever imagined. A story where our entire cosmos is just a single leaf on an infinite tree of reality. The search for the faintest cosmic whispers has pushed the boundaries of what is technologically possible, and those advances ripple outward, transforming other fields in unexpected ways. Consider the cryogenic detectors used in observatories like the Simons Observatory. To sense the minuscule temperature fluctuations of the cosmic microwave background, these instruments must be cooled to within a fraction of a degree above absolute zero. This relentless drive for ultra-sensitive, ultra-cold sensors has directly benefited medical technology. The same superconducting quantum interference devices, or SQUID, developed to read the faint signals from CMB detectors, are now used in magnetoencephalography, or MEG, machines. These devices can non-invasively map the brain's activity by measuring the incredibly weak magnetic fields produced by neural currents, offering doctors a powerful tool for diagnosing epilepsy and planning brain surgery. The quest to see the dawn of time is giving us a clearer window into the human mind. The challenge of cosmology is not just collecting data, but making sense of it. A single CMB mapping mission can generate a petabyte of information, a number almost too large to comprehend. To find the subtle patterns in this ocean of numbers, cosmologists had to pioneer new methods of statistical analysis and data processing. These sophisticated algorithms, designed to filter out noise and extract meaningful signals from colossal datasets, have become foundational to the field of machine learning. The techniques used to distinguish the primordial B-mode signal from galactic dust are now applied to everything from improving speech recognition software to analyzing financial markets for trends. The need to understand the universe has forced us to become better at understanding information itself, driving progress in the era of big data. Perhaps the most profound cross-pollination occurs between cosmology and particle physics. The early universe was a natural particle accelerator of unimaginable power, achieving energies that our largest human-built colliders can only dream of reaching. By studying the cosmic microwave background and the primordial abundances of elements, we are effectively conducting archaeology on these ultimate high-energy events. The properties of dark matter and the potential existence of new, undiscovered particles are written into the blueprint of the cosmos. Cosmological observations provide the only viable testing ground for theories that operate at these grand scales, forcing particle physicists to refine their models and search for new physics. This creates a beautiful feedback loop, where discoveries at the largest scales inform our understanding of the smallest building blocks of reality. The story of cosmic origins is not a solitary academic pursuit. It is a catalyst that accelerates innovation across the entire scientific landscape, proving that in looking up at the stars, we also learn to see our own world and our own potential more clearly. These cosmic portraits are far more than scientific data. They are a mirror held up to the deepest past, revealing a heritage that belongs to every single person on Earth. When a child stands before the modeled, full-sky map from the Planck satellite in a planetarium, they are not just looking at a colorful image. They are seeing the infant universe, a cosmic baby picture that is also their own origin story. Museums around the world have transformed these datasets into immersive visualizations, allowing visitors to literally reach out and touch the hot and cold spots that seeded the galaxies. This act of public engagement is not a side project. It is a core part of the scientific endeavor. By translating complex data into a shared cultural experience, we build a bridge between the abstract world of theoretical physics and the innate human desire to understand our place in the grand scheme of things. This connection fosters a crucial scientific literacy, an appreciation for the patient, collaborative process of discovery that stretches from a puzzling antenna hissed to a satellite orbiting 1,000,000 miles from Earth. For a young student captivated by the story, this can be the spark that ignites a lifelong passion, inspiring the next generation of engineers, astronomers, and cosmologists who will build the even more sensitive detectors of tomorrow. The most profound lesson, however, is one of unity. Every atom of oxygen we breathe, every particle of iron in our blood, was forged in the nuclear furnaces of long-dead stars. The calcium in our bones and the carbon that forms the foundation of life were scattered across the galaxy by stellar explosions, eventually finding their way into the planet we call home. We are not just living in the universe, we are a product of it, a way for the cosmos to become aware of itself. This story, which begins with the faintest quantum whispers imprinted on the first light, is ultimately our story as well. Yet the grand ambition of peering back to the dawn of time carries a profound earthly responsibility. These monumental projects, like the Planck satellite or the upcoming CMB-S4 Observatory, are not built in isolation. They represent massive investments of public funding, international cooperation on a scale rarely seen, and the dedicated work of thousands of scientists and engineers over decades. This scale naturally raises a crucial question, one that moves beyond pure physics and into the realm of ethics. How do we justify the immense cost of studying the cosmic microwave background when there are so many pressing needs here on Earth? The answer lies in recognizing that this is not an either-or proposition. The technological innovations driven by cosmology often find critical applications elsewhere. More fundamentally, the quest to understand our origins fulfills a deep human need for meaning, a cultural and intellectual endeavor that has defined our species for millennia. It is an investment not just in technology, but in inspiration, pushing the boundaries of human knowledge for generations to come. This justification, however, demands a commitment to responsible stewardship. The cosmological community has embraced this through a powerful principle: open data. Following in the footsteps of missions like COBE and WMAP, the Planck collaboration made its entire treasure trove of data publicly available. This means a researcher at a university in Chile or South Africa, with limited funding for their own telescope time, has the same access to the universe's baby picture as a scientist at the world's most prestigious institutions. This policy democratizes discovery, allowing brilliant minds everywhere to sift through the data, asking new questions and making unexpected connections. It transforms a single mission into a global resource, maximizing the scientific return on a public investment and fostering a truly international spirit of inquiry. As these projects grow ever larger and more expensive, the ethical imperative only strengthens. The community must continually balance the thrilling drive for discovery with a mindful approach to collaboration, ensuring that the quest to understand the cosmos remains an inclusive and equitable human enterprise, one that reflects the best of our collective potential. This grand synthesis is a testament to the power of a simple idea. A hot, dense beginning followed by expansion and cooling predicts a specific relic glow and a specific mix of light elements. The astonishing fact is that we have found both, and they match the predictions with breathtaking accuracy. The faint hiss in a radio telescope, the precise percentages of helium in ancient stars, the leopard spot pattern on a full sky map, they are all chapters of the same story. It is a story written not in words, but in the fundamental language of physics, a language of temperature, density, and energy that we have learned to decode. This narrative connects the unimaginably small, the quantum fluctuations of a nascent cosmos, to the unimaginably large, the vast cosmic web of galaxies we see today. The invisible hand of dark matter sculpted that web, while the mysterious push of dark energy dictates its ultimate fate. Every piece of evidence interlocks, each discovery reinforcing the others to build a picture of stunning coherence. Yet for all its success, this standard model of cosmology is not a final answer. It is a framework, a robust and well-tested scaffold upon which we can build our questions. The lingering anomalies, like the Hubble tension and the large-scale asymmetries, are not cracks in the foundation so much as doors to the next room. They remind us that our cosmic story is still being written, with every new observation adding a sentence, a paragraph, or sometimes an entirely new chapter. The journey from echoes to evidence has given us a map of reality, but the most exciting discoveries often lie just beyond the edge of the known. This journey from echoes to evidence stands as a towering achievement of human curiosity. We have learned to read the faintest whispers from the dawn of time, transforming a uniform hiss into a detailed history of our cosmos. The cosmic microwave background is far more than ancient light. It is a time capsule, a Rosetta Stone that allows us to decode the universe's first moments. It tells us the age of everything, the recipe for its contents, and the shape of its destiny. Yet, with each profound answer, we uncover deeper, more fundamental questions. The mechanism that drove inflation remains hidden. The true nature of dark matter and dark energy continues to elude us. We are left staring at anomalies in the data that hint at physics beyond our current understanding. The search is far from over. A new generation of observatories, both on the ground and in space, is being built to push these boundaries further. They will listen even more closely to the ancient light, hoping to catch the swirl of primordial gravitational waves or to find the crack in our standard model that leads to a new theory. As Carl Sagan so beautifully noted, the cosmos is within us. We are made of star stuff. This is not just a story about distant galaxies and abstract forces. It is our own origin story. We are the universe awakening to contemplate itself. What do you think is the next great cosmic mystery we will solve? Share your thoughts in the comments and subscribe to continue this exploration.